All right, well, props to you guys for showing up. It's the first talk of the morning, so appreciate you being here. All right, so my name is Beauchamp. I work at SAIC, do security consulting, pen testing, some other interesting stuff. And I did this research with Dave Weston, who used to work there with me and is now at Microsoft. So, yeah. Today we're going to be talking about retrace. So we'll start with tracing applications at runtime and show how we can use this for vulnerability pinpointing. We'll go into programmatic debugging with a Ruby-based toolkit we wrote and end up with some generic kernels and application stuff. So first, let's talk about the background of DTrace in case you're not familiar with it. This is a kernel-based dynamic tracing framework, something that Sun built many years ago. They open sourced it under their SDDL license. It was released with Sun OS 10 back in 2005. And DTrace has since been ported to Leopard. So back in October of 2007, it was the first time that we saw this on a desktop operating system. So that's when we started to get curious about how can we use this for our exploit needs. We're also seeing it being ported to FreeBSD. It's currently in the FreeBSD 7 current branch, and will be in the FreeBSD 8 stable branch. So this guy, John Viral, ported it to FreeBSD.
Yeah, so what we're going to talk about mostly, we're going to use examples of OS X as an operating system, but really it's generic to anybody who implements DTrace. So if you've got a Ruby interpreter and you got DTrace, you can use our toolkit with a little bit of customization. One interesting thing, which I'm not sure, is I had heard in the upcoming iPhone releases that DTrace may be included. So I know instruments is supposed to be included, so that would implicitly tell you that there's some DTrace functionality. So I'd be very interested in seeing how DTrace performs on a mobile device coming up.
We've also seen it on Neutrino, partial implementation. So the basic overview here is that DTrace is a performance tracing framework. So it enables you to observe what an application is doing at runtime. This may remind you of other tracing utilities like strace or ktrace, or things that are sort of single purpose. DTrace gives you the framework to implement your own tools to either re-implement things like strace or to specify exactly what you're interested in tracing. So you do this by defining these probes and then actions that go along with the probes. So this is what the architecture looks like here. We have a lot of cooperation from the kernel. That's what the bottom of the screen is here. So you get these categories of probes like system call probes or the function boundary tracing for tracing functions within the kernel itself.
So one useful way to think about this, an analogy may be like consider an entire operating system where there's breakpoints in every strategic place, and it's just a matter of enabling those breakpoints to get some type of instrumentation in that area. So it really is like having a system with a debugger attached from top to bottom. So that's kernel, subsystems, the kernel itself, I/O, networking, user applications, and at any time you can just say, hey, I want to know what's going to happen when that particular point of instrumentation is hit.
So there's this user land library here, libdtrace, which is utilized by a number of applications, generic OS applications, but then also the DTrace user land binary itself. So what we're interested in doing is writing these DTrace scripts, which will be run through this whole environment. So we write these little DTrace scripts in a language called D. The authors describe it as a syntax of C. So you basically specify your actions that get compiled into some intermediate form and then run with cooperation of the kernel as the application is being traced. Now, D actually turns out to be quite limiting because it doesn't have control flow. So there's not things like loops, which really limits what we can do in our logic. So it's really meant for taking measurements and recording, doing comparisons and small amount of recording. And there's good reason for this, right? You don't want to be the kernel and accidentally hand off control to some script that's hooking a function that's never going to return, because the kernel will never get control and then you're completely screwed. So you'll see that safety and performance are major priority requirements in the design of DTrace. So sometimes this works to our advantage because we care about performance when we're doing tracing. And sometimes it's not to our advantage because you'll end up dropping probes and stuff.
So that's probably one of the main problems solved by our talk and by our framework is, of course, we've got this really cool framework that does tracing of the entire system, but it's primarily designed for troubleshooting, for performance, and for overall debugging of production systems. So Sun created this as a way to say, hey, we can send our consultant in there on your live production system, and he can tell you what's leaking memory, what's sitting on CPU for too long, without you having to set up a completely separate system, which you would have normally had to do, recreating your production environment so that you can debug because it's too dangerous to attach a debugger to Apache or your SQL server in live. So what's happened is that, of course, that gives us a lot of power as reverse engineers, but because of the safety and performance considerations, you'll see that we kind of have to figure out and do a MacGyver thing around some of those roadblocks.
So the bottom line for performance is that there really is no impact when DTrace is not active. And when it is active, it's been streamlined to be most efficient. Okay, so there's a million of different things we can do with DTrace. And a lot of them have been implemented with these singular tools like strace and truss, and so you can go re-implement those if you want, or focus in on exactly what you're curious about in an application. So the real takeaway here is that DTrace combines system performance statistics, debugging information, and execution analysis into one small framework. So it turns out to be very useful for us as reverse engineers because we want to answer very general questions about behavior, but then we also want the ability to zoom into a specific situation or condition and inspect exactly what the application is doing. We also have the ability to trace the application as it's interacting with the rest of the system, or to trace multiple applications at once. So before you run off and all write your own DTrace scripts, there's a lot of work that's already been done out there that you can reference. So there's this thing called the DTrace Toolkit, which includes pretty much every kind of script you'd want for monitoring performance, things like I/O, disk I/O, system call tracing, things to snoop file input and output, which is interesting, and monitoring file activity.
Just to give you an idea of how powerful DTrace actually is, if you noticed in the 10.4, so the Tiger release, there's a utility that's been around since the creation of OS X called ktrace, and that was your main system call tracing tool. Well, that's been replaced in Leopard with like a 50-line D script, and it performs about 60% better. So you can actually replicate any of those tools that we showed on the previous slide. The nice thing is that you have a custom a singular interface to all of these tools. So instead of having to write a custom bash script where you launch strace and then switch to GDB, you have all this in a sort of uniform, very elegant framework that you can use to create sort of monster tools. And you'll see a lot of that in the Sun DTrace toolkit, some really great examples.
Okay, so let's take a look at some simple examples. This is a one-line DTrace script. This is a script here. You got the probe definition and the action itself. Basically, what this is going to do is trace every application across the system, recording the number of times that each application makes a system call, regardless of what that call was. So the output from running this script for a short period of time shows us that, syslog made one system call, cupsd made 4 system calls, and VMware made almost 7,000 system calls. So what we might be interested in doing here is drilling down and focusing on VMware and saying, okay, which system calls is it making?
Or what the arguments to those system calls are.
Here's another example. This shows a small DTrace script that it hooks every open function, every open syscall function at the entry point, and then simply prints out the executable name and the first parameter of that function, which will be the file that was opened. So output from this might look like this. It shows finders opening a plist file, VMware is opening dev urandom, and so on. So these configuration files and these resource files are being opened by these different applications.
So the cool part is you can start to use what are called predicates, which we'll explain in a second, where you can say, when this system call happens with this particular argument, which files are then open. So you can get some really deep sort of nested if-else type of statements to really zoom in on the particular area of the application that you're interested in, all without having access to the source code.
Okay, so to review some of the terms we've heard here, there's probes, which are your points of instrumentation, or you can think of them as your points of hooking. There's these providers, which are just logical categories of probes. And then there's predicates, which are conditional statements. So these are evaluated true or false, and then the action is carried out or not. So you can hook something and then decide not to do something. This is, if you've seen awk, the syntax is much like awk. You specify some condition, like, the line, awk is processing a line. So the line has 4 elements to it, and then the action that goes along with that. And if there's 4 elements in the line, then print out the first one. So it's a hook, a predicate, and an action. So the way the syntax looks is like this. You've got your probe, which consists of the category, the module, which is usually a library, the function name, and then this last field is usually the entry point of the function, the exit point of the function, or every instruction within that function. The predicate is the conditional statement that's evaluated to true or false, and then the action is carried out depending on that predicate. Okay, so let's talk about how we utilize this for our reverse engineering tasks.
Okay, so you probably already have some ideas of how this can be used for reverse engineering. You can get all sorts of information about how a particular application you're interested in either testing for security or understanding, just a general understanding of how it's interacting with the system as a whole. So you know what syscalls are going on, you know when it's making IOs, what files it's touching, you know all sorts of things about it. So the idea here is that you can really quickly, by either using a script that you've created beforehand or tailoring a script to the behavior of that particular application, you can get an idea of how it's working at a sort of a top level, and then you can zoom in on the areas that maybe are part of the attack surface, or just going to give you some general ideas about the security of the application itself. So it's very useful. The other thing is you can use predicates. So, for example, you may want to trace till a function gets an input from your fuzzer, right? If string copy is getting 5,000 A's, maybe you want to trigger the debugger at that point and say, hey, I want to see what's going on here. So it kind of releases you from that idea of having to say a million breakpoints which kill the performance and change the memory layout of your application, and will only trigger a debugger when there's a specific incidents that you're interested in. So the way we like to think of it is as a rapid development framework for reverse engineering tasks and tools. So the way we use it is we're lazy reverse engineers, right? We're lazy hackers. If something takes too long, if you have to attach the debugger and you have to write all these conditional breakpoints, you're going to get tired. But the idea here is that we've really sped up the exploit development time, the vulnerability assessment time, by giving you the tools that can really tell you what things you're interested in very quickly. So you can script things, you can attach and unattach from an application as it runs. Because it's running in the kernel, you're not interfering with the memory layout at all. So if you've ever experienced this while using GDB, you set up an exploit, you get it working. The second you detach GDB, the memory layout's different, so now your shellcode doesn't execute and it crashes instead. You don't have those problems with DTrace. So the idea is that you can refine what you're interested in or what you're doing without any performance penalties or slowdown at all.
Okay, so let's look at some of the simple things we get with DTrace that are provided for us that we would have to implement ourselves if we were to write our own custom tool. So this is things like control flow graphs, symbol resolution, call stack traces, and the ability to examine function parameters, and both in user space and kernel space. So here's an example of control flow. We've got the arrows to the right indicate that the function is being called, and then to the left indicate that the function is returning. So from here, we can get a sense of which functions are calling which functions and when they're returning. This is the dynamic call graph. Here's an example of a stack trace with all our symbol information. So this is the FTPD main function right at the bottom here, and it's call stack trace all the way up to the top where it's calling string compare. So not only do you see the library, but also the function name and the instruction offset within that function. So it gives us the ability to pinpoint exactly where we are in the execution. We can quickly and conveniently record the function parameters as well as the return values. So this shows us it's recording the first argument of the function. So if we're hooking string compare, it simply prints out what the first argument is special 1.
The syntax here actually gives you a little bit of idea of how DTrace is working. If you notice, the syntax there is copy and str, because what you're actually doing here is you're asking the kernel to copy information from userland into the kernel to give you information. So the way a breakpoint works is by modifying the target process memory, right? It writes an int3 instruction, and that's what causes the execution to pause on the CPU, and the CPU calls back to you, says, what do you want to do? This is very different. It doesn't modify any instructions in any way or cause any pause in the execution of the program at runtime. So you're getting a great view of everything that's going on in this application from the kernel's perspective without disrupting it at all. So what you see is what you get here, and that really becomes useful. When you're attaching a fuzzer and you're annihilating this thing and causing tons of threads to happen, if you were to have a debugger attached, right, you'd be hitting breakpoints every 2 seconds and having to continue and really slow down. With DTrace, you don't have those problems. You can easily monitor and instrument a fuzzer without really any performance costs at all.
Okay, so we also have a convenient way to reference all the CPU context. So with this global uregs variable that DTrace provides us, we can print out values like EIP, EAX, and all of the CPU registers.
That also works on more architectures than just x86. So if you saw that the EIP is actually abstracted, so it works on PowerPC, Spark, x86, a couple other architectures.
So this is a cute little example that hooks the uname system call and then changes what it's going to return, right? So this would be kind of a pain in the ass for you to write some little rootkit style thing that's going to hook this function and modify the return value, but DTrace lets us do it pretty easily. So we record the pointer to the buffer on the uname entry point, and then on the return point of the function, we just overwrite that buffer with our own information. So this shows us that Windows is running on a PowerPC architecture in 2010. Here's another small example that shows file process snooping. So here we hook the write entry point and the write return point. So same idea, record the buffer and then print it out when the function returns. So this would allow me to sniff all of the output from David's terminal or any other application. Okay, so hopefully this gives you the context of what we can use this for. We're thinking about monitoring the stack, about doing code coverage metrics. We could use those metrics to automate feedback to the fuzzer to tell it to adjust inputs in certain ways, monitor for heap corruptions. That's a really useful area. So we're going to go over some of these now.
So I talked to you already a little bit about the difference between debuggers and DTrace as a framework for monitoring an application, but just quickly, it's really important that you don't think of it as a debugger. There's things that GDB does that DTrace will never be able to do and vice versa. So one thing that DTrace doesn't do well is exception handling. So if you've got a trace script attached to an application and you trigger a buffer overflow, DTrace is not going to say memory error, read or write error at a particular address. It's just going to stop because remember, it's designed for safety and performance. So as soon as something goes bad, it just detaches from the process and drops the probe and says, I don't want to have anything to do with it. But that being said, it's infinitely more flexible for conditional breakpoints or conditional instrumenting than GDB is. So what we find is that using the two together is going to give you the optimum bang for your buck. So what we'll do is we'll trace to a condition that we're really interested in. When we see that a buffer overflow is about to happen, we'll send the stop signal to the application. We can attach GDB, let GDB continue it, and there you go. So we find that's a really flexible situation for exploit development or for looking at a vulnerability close. The other interesting thing is the comparison against strace or ltrace or some of the other tracers you know. The main problem there is I don't know how many of you attach trust to a really complicated application, let's say Apache. I mean, the amount of syscalls that are happening per second or per minute are just devastating. It's going to drive your CPU up and make it almost unusable. You don't have that problem with DTrace. Trust and some of the other tracers work by actually setting breakpoints when a system call is made or instrumenting procfs, so procfs pauses and allows you to grab the arguments. You don't have to do any of that. So Brendan Gregg did a little bit of study. You can check it out on brendangregg.com where he studied the performance of a trust implemented in DTrace versus actual trust, and DTrace is about 68% better performing. So you hardly notice system call tracing when you have a binary instrumented. Again, some of the limitations here are that DTrace is designed as like a command line real-time tool, so it really works on only standard in and standard out. So we had to do a lot of trickery with Ruby to parse the standard out to get things into arrays and to sort of retrofit data structures onto the output of DTrace. So if you're hoping to use it and you're just going to get an array of of arguments that were touched by your fuzzer or something like that, you're not going to get it without our tool. Here's a couple other cautionaries. Like we said, it would be really hard to use DTrace as a serious security tool. We'll talk a little bit later as creating a HIDS tailored to a custom application. The problem here is, remember, it's designed for performance and security. So if you start to get a lot of errors, DTrace will just back off and start to drop probes. So if you were going to use this as a dependable, hey, I need to know if anything bad ever happens on the HIDS, if an attacker was to just spray a bunch of data at the application and cause it to slow down, DTrace would just detach and it would go undetected. So those are some of the options that are some of the things you have to deal with when using DTrace. Let me start on this.
Okay, so let's talk a little bit about what we did with DTrace, combining it with Ruby and combining with some other Ruby-based tools and a programmatic debugger framework that we've also written into the combo. So what we did was we hit certain roadblocks with DTrace where we just couldn't do certain things that we really wanted to be able to do. And we started looking at taking Ruby and combining these two things to give us better logic processing so that we weren't just doing the data recording. So we came up with retrace, which is a combination of these two things. So it utilizes this libdtrace Ruby bindings library written by Chris Andrews to allow us to access DTrace from Ruby. So then what we do is write common tasks in Ruby that build these little DTrace scripts and send them off and run them and then handle the results. So with another aspect of this is to utilize IDA and its static disassembly power with this runtime dynamic tracing, right? So now you get both the dynamic world and the static world together. There's a plugin called IDA Rub for Ruby. And this has two parts. There's kind of the Ruby client module, and then there's also the IDA server part, the IDA server plugin. So what we do is we run IDA on a Windows box in a VMware, and then over the network we can communicate to it with our Ruby-based framework. Saying things like color this instruction, annotate the disassembly in this way, or pull down the disassembly information itself.
So this kind of gets around the lack of IDA GUI support on certain operating systems and architectures, right? If you're using Solaris, unless you have a Windows box next to you, you're not going to be able to combine static disassembly with runtime. By using the network XML RPC between IDA and DTrace or retrace our framework, we're really opening up the merging between statistical analysis, our static analysis, and runtime analysis, and it makes a really powerful combo. The other thing is we skipped over MetaASM, but MetaASM, which is a Ruby-based assembler, disassembler, has some incredible power itself as part of the Metasploit framework. And you can do things like write PE files from memory. You can create assembly and disassemblies in Ruby, write them to ELF files. So you can do quite a bit of stuff, and that really comes into play and becomes really powerful with malware analysis, automated unpacking. There's just so many applications. And that's why we really picked Ruby as a framework, because we feel like the integration of all these tool sets is really the future for automating a lot of the tasks that used to be really manually intensive and hard to get done.
So what we found here is that by using this framework, both the tracing and also the static analysis, it's allowed us to decrease the amount of time it takes to do the analysis, to write successful exploits. We also had limitations with just doing tracing. We wanted to do things that were more like debugging. So we went ahead and wrote C Ruby bindings to wrap OSX's mock API, the debugging API, and the ability to utilize that from Ruby. So now we can do things like set traditional breakpoints, search through memory, change the memory permissions on different memory segments. We can search for specific opcodes and segments we know are executable. So this really provides us the third element. So we've got the tracing part with retrace, the disassembly with tools like IDA and MetaASM, and then this debugger ability. So the way I guess I sort of covered this already, but the debugger really provides us a wrapper around the native debugging API, which allows us to do this stuff and like walk memory segments and catch exceptions and do symbol resolution and all that.
Yeah, a lot of people sort of have the idea that Mac OS X is really just, Mac OS X is really just BSD, but that's not the case. You don't have the standard ptrace API like you would on every other POSIX system. It's really Mach at the core. Even though there is a BSD subsystem, most of the intensive sort of system internals and system programming you're going to be doing is in Mach. So we had to have the fun job of learning how to send Mach messages back and forth to the kernel and stuff. But we've given that to you here, so you really have a flexible marriage between the best parts of debugging and Ruby and the best parts of retrace and DTrace.
Okay, so here's how it all comes together. There was this iPhoto format string vulnerability. We ran into Rob Carter and Nate McFeeters back in DC, and they were showing us this thing and curious on how we could use DTrace to, really pull out the information we need from the application at runtime in order to understand how to write the exploit. So we threw all these tools together and we were able to, trace through all of the different printfs that happen in the application until like the 2000th one, which we were actually interested in, trace until we hit that spot, and then do the application analysis, whereas just setting a breakpoint would have took forever, iterating through each step. So we used the predicate feature to say, only stop the application when one of the variables has this %25 in it. So the way we envision this with the framework is sort of like this. At the top here is the code for specifying the DTrace within Ruby, the DTrace Ruby lib to say, hook this vfprintf function, and if the argument is this %25in, then stop the application. So we go ahead and kick that off, and then we connect to our IDA Ruby server, and we pull, once it's stopped, we pull down some information about the function. Like we want to see the disassembly of the function itself so that we can find the return instruction and set a breakpoint there. Then we continue the application, and we have a callback function for when our breakpoints hit. And then we continue the application. So then at the end of the function, we hit the breakpoint, and we want to inspect memory at that point to say, okay, is the overflow aligned properly?
So the cool part about this is is not quite automated exploit development, but it's about as close as you're going to get, right? So he kind of shaved over the fact of that you had to sit there and hit continue 1,000 times on every printf that could possibly happen in iPhoto. Well, imagine doing that during the exploit development process. So literally, this script could save you several dozen hours of the lifetime of an exploit developing it. And in fact, when Nate and Rob brought this to us, they were like, we can't even stand GDB anymore. This is killing us. And so we actually came up with this script all sitting together at a bar one night, and it's actually worked out pretty well. So when you're done with the script, you know exactly what instruction you need to overwrite, and you can then use our opcode searching feature to just find instruction in executable memory that's going to point you right back there. So, 2 steps beyond this, and you have arbitrary code execution.
All right, so here's another interesting idea, right? We know there's something funky with ASLR on OS X, and we may be interested in trying to analyze that. So one thing you might want to do is, you found a bug in an application, you're trying to figure out how the memory works so that you can use specific values in a return to libc style attack. So what you can do is start up the application and then do some symbol resolution to figure out what interesting functions you want to use are at what locations. But these addresses will be randomized, or they should be, after each run. So you search memory for some sort of function pointer to one of those addresses. And then you restart the application after it's been randomized, and you search again for references to those same functions. So you try and find some spot in virtual memory that always contains a pointer to that randomized address. So this is the sort of task that you could also automate with this framework. So our framework's up on popopred.org. We're going to stick it up there tonight. Retrace is already up there. We just need to add a red bug. Okay, so let's look at monitoring the stack. So what we're going to do here is assume we have a classical stack buffer overflow. We're going to trace our application until that instant and then print out all the information that we care about. So we want to do this to pinpoint exactly where the vulnerable function is.
Yeah, this is a situation where maybe you're fuzzing an application and you get an exception from whatever debugger you have attached. You look at the stack and it's filled with A's, right? But who overflew, where was that, and how can you leverage that to do either understand the vulnerability itself so you can protect yourself and understand how important the patch is, or you want to leverage it for arbitrary code execution. And it's definitely not a 1, 2, 3 step from getting a Stack Overflow to understanding exactly the nature of that bug itself and whether it's new and what the problems with it are.
All right, so here it is in one probe. We're going to hook every function and every return address, right? Or we'll hook every function, every module. If our EIP or the next instruction pointer is 41414 the encoding of a string of A's, then we're going to stop the application saying, okay, something bad happened here, let's check it out. So, this works in the generic sense where you're overflowing with large strings of A's, but that's not always the case, right? We want some more generic solution. So our approach here is to, at function entry, record what the return address is on the stack, and on function return, check what EIP is. Is our next instruction equal to that return? It should be. If it's not, we know something went wrong, right? There's some sort of overflow that corrupted the return address.
We're going to give you a little tip that might save you several hours that it cost us. You see that second slide point there, uregs RESP and not uregs RESP? That is a big one. On the Core 2 dual architecture, which is a 64-bit architecture, they don't call it ESP, they call it SP. And if you confuse those two, it's going to cost you several hours of problems.
Yeah, so RSP is the architecture-independent reference to that. So we had some problems with tail call optimizations that happened at compile time, and also some functions that DTrace can't trace. So this kind of threw a wrench in the problem. So I won't bore you with the details of tail calls, but the basic idea is that some functions don't require their own stack frame. So although you're calling a new function, there's no new stack frame on the stack, so then it kind of messes up, well, how do you think about the return pointers and all this stuff? So DTrace has a particular way of dealing with that, and you just have to know what it chooses to do. If you're curious, I'll tell you all about it. But the basic idea is that instead of comparing IP, when we enter a function, we record the return address on the stack. When we exit the function, then we look at that same spot in memory, see if it's the same. So we have this problem with functions we can't trace. Our solution is just to ignore them because they're usually not the functions that we're interested in anyway. So it turns out DTrace has some problems with tracing functions like when they're inside jump tables, and so it chooses to just ignore them. We'll trace the entry point, but then it doesn't know how to do the return point. Our basic way to determine which functions can't be traced in this way is to say, show me the entry points for all the functions that you know about, and show me the return points. And then we look for mismatches, right? Because some will be in one list and not the other. We just exclude those functions with predicates. So let's take a look at how this works. Have to double click it?
Yeah. Go back. Should be playing now. There you go.
Oh, it plays up here. Okay. So what we're going to do is run an RTSP QuickTime exploit like we've seen a lot of these this year, right? So it's listening on the local host, and then we're going to start up QuickTime and have it connect to this malicious server, and then Stack Overflow is going to be delivered. So, but what we're going to do there in between is attach retrace to this application so that we can watch the overflow as it happens. So we load up QuickTime here, and we're going to attach retrace. So we start up the Ruby environment. Now this is actually like your standard IRB, right? So you can go ahead and specify whatever kind of Ruby code you want. So there's all our commands, right? Like searching memory and attaching a debugger and stuff like that. So what we're going to do is we're going to specify the PID and then run the Stack Overflow tracer on QuickTime. Now we go ahead and connect to the malicious server, which is going to deliver the payload. So a lot of things happen all at once there. The application, it opened up a window to read that. The payload was delivered down here, and then retrace stopped the application. So it's actually halted. So we get all this information printed out about the context of the application's current state. We get a basic message about a Stack Overflow occurring. We see the exact module where the overflow occurred, the particular function, what we expected the return address to be, and what it actually was. So in this case, it's, you know, OX17 blah, 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 but it was actually deadbeat. So probably a problem. So here's all the CPU registers. You can see in this situation, a number of them were overflown. ESI, the base pointer, and so on. So here's our stack trace. You can see again module name, function name, followed by the exact instruction offset within that function. So from here, we might be interested in doing something like, you know, attaching a debugger and examining the memory space, searching for instances of particular strings we want to use in a return to C style attack. So what I'll do is I'll show how that happens with a different application here. Let's use Adium. So Adium's a chat client, right? I just picked it randomly. So imagine that we're going to do a simple return to libc, and we need to use bin bash as one of the parameters to some system call function, right? We need to know a location in virtual memory at this moment where bin bash is located. So what we're going to do is dump all of the memory, all the virtual memory segments, and then search through them. So in retrace, this works by taking each segment and dumping it to disk. With Redbug, we've actually implemented it, so you don't need to dump it to disk. So here we search for bin bash, the string bin bash. Looks through all the memory segments, and we get about 5, 6 locations. So let's just attach a debugger and then check what the value at each of those locations is, just to make sure that it's usable for our situation. So in retrace, what attach debugger does is just it stops retrace and then attaches GDB to the process. So here we can see it's really in the same state. Now let's inspect memory at the first location. We can see that this is a string that starts with bin bash, but it's got all this other junk on the end of it, right? This is not going to be useful to us. So we can inspect the next memory location. It turns out to be bin bash null terminated. So this is what we'd want to use, right? And as well, the other 5 locations are all bin bash. So those would be potentially used.
So the idea here is to get around data execution prevention, you can manipulate to make a system call. In this case, if you make the system call /bin bash, you're going to get a shell. That's a bash shell. So that's why it's so interesting on there, because we can't just run code off the stack anymore. We'll have to return into mprotect or bin bash, something like that, to actually get leverage getting a shell in the box.
Okay, so some other things we can do with retrace, you know, instruction level tracing, well, that'll give us the ability to do code coverage. We're very interested in that. So let's briefly talk about it. The idea is pretty simple here. DTrace gives us the ability to print out the address of the instruction at each point. So we just print them all out and then map them into IDA, and we can visually represent what code coverage looks like during a particular run of an application. So that's the whole approach. It's really pretty simple. There's things we have to deal with you know, when we're tracing instructions that are in a library that's mapped like deep in virtual memory space, and then in our disassembler to start, it's mapped at location, you know, OX1000. So we just have to deal with, you know, mapping those offsets. So it's not really a problem. You can just either trick your disassembler into specifying exactly where the starting point for the address is, or you can do the offsets in Ruby itself. You do have some issues with performance, right? Because tracing every instruction can be kind of heavy load on the system. So you just scope to only trace particular libraries or applications you're interested in. So what this turns out to look like, the real fruit of it is this. You get a function call, graph, and the particular blocks that were traced or run during the application are highlighted. So you can say, okay, cool, I missed this whole section of code. Let me figure out how to tweak that jump to access and test the rest of it.
Yeah, so maybe per fuzzer run you would change the color and then you end up with like a really cool rainbow or a mandala. But you know on every sequential fuzzer run whether you're hitting code that you weren't before.
You also do stuff like this, you know, with simple dot graphs. Show what the system call graph looks like at runtime. So you may know that something was patched here, and there was a vulnerability here, and the patch was applied to this function. So they're doing some sort of input sanitization here, but there's another code path to get there. So let's look at how we can get down here and access that vulnerable function again without going through the patched function.
All right, so I'm going to tell you about how to use DTrace to write heap overflows. So how many of you familiar out there with the term heap spraying and that type of stuff? Show of hands. Okay. So heap spraying is all about heap determinism, right? Controlling the determinism, the allocation patterns on the heap. So you can set this heap up so your overflow gets arbitrary code execution. If you want to know more about it, the Immunity guys who have a booth here wrote a great paper on it called Debugging with ID that tells you everything you want to know about advanced heap exploits. But the idea here is that in the past there was a primitive called the write for, which essentially gave you a generic technique for exploiting a heap. Well, that's gone. There's heap protections, and it never existed on BSD because they keep their metadata out of band. That is, there's no function pointers that you can just overflow into to leverage arbitrary code execution. So what that means in plain English is that you have to understand a lot about how the application allocates things on the heap in order to exploit something successfully. So you're looking for function pointers, you're looking for any kind of application-specific data that you can overwrite with a heap overflow that's going to cause you to own the application. So on other platforms, there's lots of tools to do this. Immunity Debugger is a great one on Windows. Gerardo Ricarde from Core wrote a great OpenGL visualizer of the heap that's based on Trust that I think works on Linux and works on any of the BSDs and Solaris. So you have stuff there. The problem was you really had nothing on Mac before this that could help you do that. So the idea here is that we have these arbitrary hooks on any function in the system with DTrace, right? So let's use them to keep track of what the heap looks like and what are the contents on the heap. So quickly, you can, of course, you can use Apple's standard instruments tool for memory leaking to identify double frees and double mallocs that are going to allow you to, maybe you could leverage that for arbitrary code execution, spot off by one errors, and you can do all kinds of heap visualization. So the comparison to something like LTrace, which could also hook malloc operations, is LTrace is like Bonds on the Pirates, and DTrace is like Bonds on the Giants. So it's LTrace on steroids. And the idea here is that you can create a heuristic for your specific application. Remember I said it's all about application-specific data. You could create a heuristic that says, if this pointer is ever on the heap next to somewhere that I know I can already overflow, then there's my exploit. So you can do all that kind of really interesting stuff. There's tons of tools on OS X that'll help you do this. That'll set up guard pages on the heap so you know if you've corrupted it. But none of them are going to allow you to have the application-specific intelligence that you need to really write these sort of advanced heap overflows. So quickly, this is what a directed graph. If you were just interested in what some of the allocation patterns are, you could quickly create a graph of the allocation patterns. Included in DTrace itself, though, we've created an automatic heap smash detector that'll instrument IDA. And basically how that works is we keep track of every allocation made to the heap, all the pointers on there. And if anybody ever string copies memory or does a mem copy onto a chunk that we know about, so we know the size and the location, and that write is too large, we know there's going to be a heap overflow and rewrite it into IDA. So let me quickly show you. That probe would look something like this. So in this case, we're looking at the entry to string copy, we're looking at the arguments, and then we'll check that probe there against our known locations in the heap, and we'll let you know if they overflow. So I'll show you a quick video there. Yeah, no, I'm jumping through here. So real quick, essentially what we're going to do is show you a vulnerable C application here. It's just standard. They malloc something that's not large enough, and then we do a string copy onto it. And if you can see through the transparency in the background, we have a copy of IDA going on. So we're interested in owning this application. What we're going to do is we're going to copy a bunch of A's on the command line and hope that that triggers a heap overflow. So just to show you, and that's what it looks like, right? We've attached the heap smash, and we sent a bunch of A's in via command line. This is our IDA disassembly of the same program. So just looking around there. And we're going to fire it off, and if all goes well, any heap overflows that are detected will automatically be in the disassembly of IDA, so we'll know everywhere that has a problem in this app. And later on, you can leverage that using another DTrace script to exploit it. So here we're starting up the IDA Rube server. That's going to give us a connection to the OS X. So this is all in a VM. You can see it's in VMware Fusion. So we're setting up our server here. Go back to the command line, fire off those A's, and hope it triggers a heap overflow. So amazingly, it does catch the heap overflow. You can see there, that's the probe that found it. Tells us what EIP was, what the destination was. The interesting thing to note there is the size of the buffer was only, 15 bytes, and we copied 30. So obviously, we smashed the heap there. And now we can go into our IDA disassembly, and it will pinpoint that. So where that would be useful is if you had a browser or something like that, and you're running a fuzzer against it, you can let that run for a couple days or hours or whatever, come back to the IDA database. It's going to tell you everywhere there was a problem, and now you can sort of vet those and figure out which situation would be exploitable. So that's the comment and the marking in red there. So it's really powerful for combining static analysis and runtime. We're kind of running out of time here, so let's shift this over to where do you want to pick up?
Yeah.
We've got just about 2 minutes. So let's go to summation.
Okay. So we have some sections here on using this defensively, some things you can do to stop based on, by seeing system call patterns that it's not supposed to do. Again, you have performance issues there. You guys can check out the rest of the slides here. We also talk about doing some kernel level stuff, not particularly related to DTrace, but you see this screen and you have no idea what happened. You want to figure it out. It turns out that there's these logs that get dumped, and then they give you a lot of information, so you don't actually need to do the kernel debugging traditionally. But if you do, you have to set up a remote server, and it's kind of a pain in the ass. So let me skip to the end.
Talk about the SQL stuff.
Let me make one point here about tracing higher level application probes, because this is a cool idea. So what you can do here is like trace some action that it's a high level thing, like a whole page load or an SQL query or a DNS lookup. So these are not particular functions, but they're actions composed of lots of functions. So this makes sense for I/O performance tracing, but also for pen testers. We can use this for our own purposes. For instance, we want to fuzz an application front end that has a web front end, and then examine what's going on with the SQL database in the back. So look at the particular SQL statements, and are they sanitized or not?
So the idea here is that on the OS X platform, because DTrace is implemented in the kernel, it's really trivial for anyone running an app on OS X to add DTrace probes that will allow us to hook them. So we could hook JavaScript, SQL injection, all kinds of stuff that are beyond sort of standard memory corruption. And I'll show you real quick where you can get the code. Here you go, pop ret. Email us if we don't put it up in the next couple of days. We've been known to lag. And thank you for your time.